Hi, I'm Monal, and I will be presenting our work on decoding output sequences for discrete-time linear hybrid systems. This is work done jointly with my advisor, Professor Sriram Sankaranarayanan at the University of Colorado Boulder. So for many applications of hybrid systems, such as designing controllers for automotive engines or predicting future trajectories of UAVs in order to monitor if they enter a restricted airspace or not, or for verifying the runtime behavior of agents in a crowded space to check if they satisfy certain properties or not. We often need to know the entire state information so as to provide that as inputs to our downstream applications. However, for most systems, such information is not available directly. The state is either too expensive to observe or not observable directly. Instead, what we have access to are just noisy measurements of the outputs of the system. So if we are given a finite sequence of length t of outputs from a hybrid system as it is evolving over time with some disturbance present, then the decoding problem seeks to reconstruct the underlying state information. It estimates this or decodes the sequence of continuous states, modes that the system is in, and the transitions taken by the hybrid system when going from one mode to another. The name was inspired by the Viterbi decoding problem algorithm, which solves a similar problem for hidden Markov models. And the decoding problem is closely related to the observer design problem for hybrid systems. The difference being that we are not just interested in estimating the state at the last time step t, but we wish to reconstruct the entire history of continuous states, modes, and transitions. And for non-deterministic systems, such a history would add more information. We study linear systems in our paper, and we model them as linear stochastic hybrid automaton. Uh, Let M be the number of modes in the automaton. The dynamics at each mode is said to be affine. So is the output map at each mode. The guard sets on the transitions between the different modes are assumed to be polyhedral, and the updates on the transitions are affine as well. We assume that the initial state and the disturbance at each time step comes from some distribution. And in our work, we assumed a uniform distribution over some polyhedral region. So the decoding problem can be encoded as an optimization problem. Given a linear stochastic hybrid automaton H and a output sequence Y of length T with some noise present, the optimization problem seeks to identify a run of the hybrid automaton such that the corresponding output sequence is as close to the given output sequence as possible. The objective of the optimization problem is to minimize this distance between the output sequences under a suitable norm. We use the L infinity norm. The output sequence corresponding to a run of the hybrid automaton is obtained by just applying the affine output map at each time step for the over the continuous state variables. We call this corresponding output sequence to be the decoded output sequence y prime. In the decision version of this problem, which we call the epsilon decoding problem, we ask if there is a run of the hybrid automaton such that the distance between the given output sequence and the decoded output sequence is bounded by some value epsilon, which is a tolerance parameter. And turns out that this problem is NP complete. We can encode the decoding problem as a mixed integer linear optimization program. The sequence of continuous states and the output variables are encoded using continuous variables. The modes and transitions at each time step are encoded using binary variables. The semantics of the hybrid automaton are encoded using linear constraints, and the objective is trying to minimize the distance between the sequence of output variables and the given output sequence. So the going back, the decoded output sequence needn't necessarily match the given output sequence exactly due to the presence of noise. So in essence, what the optimization problem is doing is it's trying to identify an output sequence that obeys the semantics of the hybrid automaton whilst being as close to the given output sequence as possible. And the number of binary variables in our mixed integer linear program formulation is in the order of t times the number of transitions times the number of modes, where t is the length of the given output sequence. And the problem is NP complete because the solution explores all possible ways of assigning values to the binary variables in our problem formulation. And this leads to an exponential time algorithm in terms of the number of binary variables in the problem. So we can think of the MILP solution as being comprised of two stages. In the first stage, we can fix the values of the binary variables, that is, fix the mode transition sequence. This would correspond to picking a path of assignments in this tree data structure that we've used to depict all possible ways of assigning values to our binary variables. And once we fix the binary variables in our problem formulation, then we are only left with the continuous variables, that is the sequence of continuous states and output variables that needs to be estimated. This can be done by encoding it and solving it as a linear program. And linear program can be solved much faster with some of the fastest algorithms being polynomial time. The challenge, of course, now is how do you come up with this valuation of binary variables so that it best explains the given output sequence. What we would have to do is iterate over all possible ways of assigning zeros and ones to our binary variables. That is, iterate over all possible paths in our tree data structure and solve one linear program for each path in the tree data structure. This would mean that we need to solve an exponential number of linear programs, one for each path in our tree data structure. In order to overcome this computational burden, we propose to identify a subset of paths called the cover set such that it satisfies this desired property, which is that the cover set has enough mode transition sequences or paths so that it decodes a randomly sampled output sequence with high probability, let's say at least alpha. So if I set alpha to be something like 0.95, it means that the cover set will find a decoded output sequence that's within epsilon distance of the given output sequence for 95% of the output sequence that exists in my output space. And if we do this, then instead of iterating over all possible paths in our tree data structure, we can iterate over only those paths that belong to our cover set C, thus reducing the number of linear programs that we need to solve before picking the one with the best objective. But the problem is that there are no theoretical guarantees that C will be any less than the value of all possible mode transition sequences. However, in practice, we hope that this value or size of the cover set is much smaller than just the set of all possible mode transition sequences. The other challenge is synthesizing a cover set for a given hybrid automaton and sequence length t is co-NP complete. And even checking if a given cover set satisfies the coverage probability that we desire is co-NP complete. To deal with this problem, we borrow ideas from statistical hypothesis testing. Uh, and we synthesize and verify a probabilistic cover set by basically running this iterative loop where we sample k output sequences from our output space independently, and we check if they are all covered by our current cover set. If it's not, then we add the corresponding mode transition sequence back to our uh, cover set and rerun the testing loop. However, if all the k independently sampled cover output sequences are already covered by our current cover set, then we've successfully verified our cover set with respect to the coverage level that we desire. And we can just solve the size C number of linear programs, one for each sequence in our cover set, and pick the solution with the least objective to be the solution for our decoding problem. The value k is determined based on the level of coverage we uh, desire, and also the level of confidence we wish to have for our statistical test. The details are provided in the paper. We tested our approach and the MILP approach on a set of 7 different benchmarks. The number of state variables for these benchmarks varied from 2 to 10. The number of modes in these benchmarks varied from 1 to 400, and the number of transitions varied from 1 to almost 800. And the plots shown here depict the outputs from running our approach on 3 different benchmarks. The dots represent noisy output sequences provided, and the solid lines represent the decoded state variables. We've also simulated the decoded state forward in time using the hybrid automaton to show one possible future trajectory. We've included some real world data set and examples with control inputs as well. So apart from this, we also tested both approaches on a set of 1,000 noisy output sequences. We set the coverage probability to be around 97% and the confidence level for the statistical testing of the cover set to be around 99% and picked the value of k accordingly. What we saw was that the size of the cover set needed to obtain a coverage level of 97% on all these different benchmarks was remarkably small compared to the size of all possible mode transition sequences. For example, in the water tank, only 4,500 odd sequences or paths are sufficient to cover a tree that had 2 times 3 to the power 100 paths. And as a result, we see that on most benchmarks, the proposed approach is significantly faster than the mixed integer linear programming approach. We set a timeout of 10,000 seconds for the MILP, and on some of the larger benchmark, the MILP times out as the sequence length increases. On the really small benchmarks of with 1 or 2 modes, the times are comparable for both the approaches. And overall, the objective of the proposed approach is slightly worse than the objective of the MILP, even though the approach is expected to cover just 95% of the output sequences in the output space. In conclusion, we basically studied the decoding problem for linear systems, and we showed how it can be formulated as a mixed integer linear program. We proposed an approach where we decompose the MILP solution into fixing the mode transition sequence and then solving the corresponding LP before picking the one with the best objective. And instead of iterating over all possible mode transition sequence, we iterate over a subset called the cover set. And we use statistical tests to verify and generate this cover set. In future, we wish to apply this to more interesting data sets, including human machine and medical device data sets, and we wish to extend our work to handle nonlinear hybrid systems. Thank you.